Okay. So how is everyone today? Yes?
Okay, so the flexes for this class, I haven't seen any, just the ones that we've taken. I haven't seen any others posted.
Yeah. So that's the first thing I've got to say here. Yeah, I came to realize the problem. So this is concerning that. What we're going to do is that WEX 04 and WEX 05. We're going to make these due 7 days from now. 18, that's not right. Today's the, what, 12th? We'll make these due Tuesday, the 12th. And then WEX 06 and WEX 07, these ones, they'll be due Thursday, the 14th. No, 14th? No, today's the 12th. My goodness.
19.
Yeah, 19, thank you. Yeah, that one. That'll get us caught back up. Yes?
I was talking about the examples. You said you would post a whole bunch of the old ones.
Yes.
That's what I was meant.
And I'll do that too.
Okay.
That's coming. So it'll be. It's just like that other one. It's just another. The link I sent you is just exactly the same, except a different link.
Okay,
But
because
it's
I got all the stuff from the college algebra and
Mhm.
I've gone through that. Because that came up, but I hadn't seen anything else for this class as far as except for the waxes that you posted that we've done already. That's
Right.
okay.
All I'm saying is that you could probably, from that link I sent you
Okay.
specifically, you could probably figure out what the link is for the college for the other one. But
Okay.
I'll send it out.
Okay.
But it's in the same general area. Good. Other questions? All right. So last time we were talking about the fundamental theorem. So the fundamental theorem, to remind you, what it's saying is that if, in the first place, you know that the derivative of big F is little f. So there's another way to say this. What's another way to say this? Moving the derivative to the other side. Yeah, you can say this is the same as saying antiderivative of little f dx is big F plus c. So these two things are identical in meaning. And 2, little f is integrable on the interval a to b. Then the integral from a to b of little f dx is, so to remind you, what this is saying take the graph of f and make that same shape that we always draw, cut it into some rectangles to make an approximation for the area of that shape, then let the number of rectangles become infinite and add them all up. So what this represents, represents a summation of infinitely many infinitesimal rectangles. So in order to make this thing, you've got to make essentially infinitely many evaluations of little f. The fundamental theorem is saying that, in fact, it's not necessary to make all those evaluations on the inside of a to b. In fact, you can just measure on the boundary. You can make 2 evaluations, one at the right endpoint, one at the left endpoint, but one of the differences is that instead of evaluating little f, you're evaluating big F. And what do you do with these two evaluations? You subtract. Okay, so the fundamental theorem is saying that, among other things, this is the relationship between derivative, antiderivative, and integral. Okay. Good. So let's consider absolute value for a minute. Absolute value. Okay, so to remind you, the definition of absolute value of x is, well, sometimes the absolute value of x is x itself. So like, for example, what's the absolute value of 3? 3. And the absolute value of 1326 is 1326. So under what circumstance is the absolute value of x just x? When x is what? What has to be true about the x? When x is positive. In fact, so this would be x is positive. We can actually do slightly better also, because what's the absolute value of 0? 0. And as a result, I can make that this. So that's non-negative. Mathematicians are like the lawyers of science, right? If you take my meaning, what's the difference between positive and non-negative? Well, this one is non-negative, greater or equal to 0. Okay. But what's the absolute value of, say, negative 4? 4, right? So another way to say that is the absolute value of negative 4 is negative 4. It's kind of a weird way to say it, but just as true. So the absolute value of x is either x or it is the negation of x. It's always going to be one of those two values. The circumstance when it's negative x is when x is negative. So now that's kind of a funny way to say it. So in particular, I find that students find it helpful if I say the following. Is it possible for negative x to be positive? Sure. Yeah. What's an example when negative x is positive? When x is negative 1. Right? Because negative 1 is 1, which is positive. Okay. Good. The shape, if we were to plot absolute value, it has a characteristic shape that you're just expected to know. Its characteristic shape is a V. So it looks more or less like this. Y is absolute value of x. And here's the thing, is that locally, like if you're far away from the origin, and you're a little bitty creature, so that this is all of the world that you can see. As far as you can tell, your world, the formula for your world is just y is equal to x. That's what it looks like to you if you're on the right side of the absolute value world and you're far away from the origin. Similarly, if you're on the left side of the absolute value world and far away from the origin, what is the formula for your world? Y is negative x. Of course, for the individual that happens to be standing right at the origin, it doesn't look like just that one. or just that one, right? No matter how small that individual is, it's always going to look like a corner there. But in the same kind of way that to us, Kansas looks flat, or if you go out on calm seas, the ocean looks flat. In the same kind of way, over here, the world looks like y is x. Over here, the world looks like y is negative x. And then there, it's always going to look like a corner. All right? As a result, just as a reminder, absolute value is not differentiable at the origin. It never looks like a line at the origin. It's differentiable everywhere else. Okay, good. That being the case. Let's consider the integral from negative 13 to 26 of absolute value of x dx. So we'd like to use the fundamental theorem because it's such a nice tool, very powerful tool. But can we use it right now directly? Not really, right? So the first question, the first thing I want you to consider, can we use FTC immediately? Okay, well, in the end, the answer to that question is more or less, can I anti-differentiate that? Can we compute the antiderivative of absolute value of x? And, well, that requires us to remember there's exactly three antiderivatives that we know. We know the antiderivative of x to n dx when n is not negative 1. We know that is x to n plus 1 over n plus 1 plus a constant. So is absolute value that one? It's not that one. We know the specific case when the exponent is negative 1. So that one is somehow singled out and special. So what's the what does this evaluate to? Yeah, log of absolute value of x plus a constant. So that one has absolute value, but well, that's not relevant because in the end we're asking about can I anti-differentiate absolute value, right? So then what's being anti-differentiated is x to exponent negative 1, and no joy. The last one that we have is the exponential one. That one. So, what's the answer to the question, can we use the FTC immediately? The answer is no. No, and then essentially, because antiderivative of absolute value of x dx is not listed. It's not one of these.
Is there a way to do it? You just don't have it?
No. I take your question to mean, well, in this class we have these three, but is there one outside of this class? And the answer is no. The way we're going to do it on this page is the same way everyone must do it. Okay, 2, fine. If that's the case, then please make a sketch and evaluate the integral using area formulas from geometry. Well, we sketched absolute value on the previous page. Its characteristic shape is that V thingy. So, all right, I'll throw up a quick sketch here of absolute value. But then I'll need someone to help me figure out what further modifications I need to make so that the sketch is useful for evaluating that integral. Okay, so there's absolute value. Now, what does this have to do with the integral? Okay.
So it's simple, just divide it by 2. There is 0, add how much it is.
Okay, let me be more specific. So, the geometric interpretation of derivative is slope of tangent line. And the geometric interpretation of integral is the area of a shape. And my question is what shape are we talking about?
Rectangle. Oh,
2 triangles? Where? I don't see them. What 2 triangles? Okay, so I need to mark negative 13. So I mark negative 13.
Line up and wherever it intersects that.
All right, like this? Okay.
And we do the same for 26.
For 20, for 26? Okay, so then what, I agree entirely. And what shapes are we talking about? The 2 triangles, right? So in the end, the integral is talking about those 2 triangles. So if we could find the area of those 2 triangles, we'd be finished. Okay, good. So let's do that. What's the base of this triangle? 26. And what's the height?
26.
Also 26. And how'd you figure out also 26?
Because it's a 1-to-1 slope.
I agree. Alternatively, because this is x is 26 right there, this height right here, needs to be y is equal to the absolute value of 26, which is 26. Okay, good. So this one is base 26, height 26. What's the base of this triangle? 13. And what's the height of that triangle? Also 13. And again, the reason why it has height 13 is because that's y is equal to the absolute value of negative 13, which is 13. Okay, so now we've, got out our ruler and measured stuff. We can see that it's 2 triangles. So this is telling us that the integral from negative 13 to 26 absolute value x dx is, well, equal to the area of each triangle added up together. So 13 times 13 over 2 plus 26 times 26 over 2. And then, whatever that turns out to be. So that's 845 over 2. Which, if you cared to do it, would be 422.5. Okay, so any question about that? Yeah?
If you wrote a function that gave you the area under the 2 triangles, would that just be a regular old function because you can't take the derivative and get back to the original function?
I think I understand your question, and remind me. We'll do that next. Okay. So I'm just going to put that on hold for 5 more minutes. Okay. So then 3. So we evaluated the integral one way. So now I want you to evaluate the integral in another way. So evaluate the integral by splitting into pieces, by splitting it into pieces, and using the FTC on each piece. So we did an example like this last time, and to remind you what that's about, that's saying that the integral from a to b of little f dx, again, conceptually, we've got this little picture here, a to b, like so, and this is the plot of y is f of x. The integral represents the area of that shape. And, well, a thing about areas is that if you cut the area right there and have 2 separate shapes, then you can find the area of the whole thing by finding the area of the one piece, finding the area of the other piece, and then adding them up. So this means that a single integral can be broken into 2 integrals like this. So a to c, that would be the first piece. And then plus c to b, that would be the second piece. Okay, so then using that idea, well, where would be a particularly convenient place to break this integral? At 0, right? Right there where the function changes its mind about how it's going to behave. Alternatively, if you're not a picture person, right there, right, where you can see that there's a change in behavior at 0. So then you could take the original integral, and you could say the integral from -13 to 26, absolute value of x dx. That'll be integral -13 to 0, absolute value of x dx, plus the integral from 0 to 26, absolute value of x dx. And now here's the thing. The instructions say we are to use the FTC eventually. And here, we still have absolute value, which means that at present, we still cannot invoke the FTC because that's not in this list, essentially. Well, here's the thing. For example, as for this integral on the right, now, the interval, that's another thing that I would like go back in time and change, if I could somehow. The words interval and integral are too close. So, sounding, I mean. Right. These x's are between 0 and 26. So that means that we are only over here. We're only on the upside. Which means that the absolute value of x is just x. So we can drop the absolute value there. Now, we can do a similar thing over here. We can say that this is the integral from negative 13 to 0, and it'll still be dx, whatever. But now what are we going to replace the absolute value of x with? With negative x. With negative x, because notice that this integral, the x's are between negative 13 and 0. So for example, something like negative 7. Then to flip that negative 7 to be positive in the way that absolute value is wont to do, well, it's going to negate the negative 7 to get negative 7. So is there any question about getting here? Because the rest of this is like turn the crank, just like kind of boring. Like if you can get here, you can do the rest of it. So is there any question about getting to this place? Okay. So from here, all right. So notice that the absolute value is gone. We have a negative there. That's multiplication by -1. That's what that really means. And the integral is homogeneous, so that's fine. As for this one, is this one of the antiderivatives that we know? Yeah, it's the power rule. With what exponent? 1. Okay, so this one is plus x squared over 2, evaluated from 0 to 26. That's what that one is. Okay, what's this one going to be? Yeah. And then evaluated from negative 13 to 0. Any question about it? All right. So now it's just a matter of plugging stuff in. So this would be what? It'd be negative 0 squared over 2, and then minus negative 13 squared over 2. Got to be a little bit careful with all those negatives. Don't leave one out. All right, so it's like this because it's the left endpoint minus the right endpoint.
So you always take the top?
Yeah, it's always the top. Yeah, this thing evaluated at the top one minus this thing evaluated at the bottom one. Yeah. Okay, and then plus 26 squared over 2 minus 0 squared over 2. Of course, the 0 squaredness is just 0. But before we go any further, I claim that you should be able to just tell me what the answer is anyhow. What is it?
422.
Yeah, is that? It's got to be that. It's got to be that because this is just two different ways to get the same answer. Okay? So, well, this would be 0. And now let's consider this. So negative 13 squared is 169 because the negative squares away. And then this negative cancels with that negative. So altogether, this would be 0 plus 169 over 2. Okay, then plus. So 26 squared would be 169 times 4. I won't even venture a guess. 26 squared. 676 over 2, and then minus 0. And then you add those up. Do we get 845? Yes, of course we do. 845 over 2. Any question about this? All right. Good. So now let's try one slightly more complicated. What about, say, this one? Please evaluate integral from 1 to 4 of 3t minus 7 dt by splitting and FTC. All right. So now, well, we've got absolute value again. And it's not going to be exactly the same as the one on the previous page. Because before, well, for one thing, the input is named t, but that's a minor issue. But at any rate, before we give the input to the absolute value, first we multiply by 3, then we subtract 7, and only then do we give it as the input to the absolute value. As a result, when you look at its plot, it's still obviously going to be some kind of absolute value, but it's not going to, for example, the point you place is not going to be at the origin. So let's figure it out. You know, just given such instructions, the best thing you can do probably is to start out by making a sketch. Sketch T. So it's still going to be like absolute value, but the question kind of is like, you know, if this is what it looks like more or less, and this is the t-axis, then the question is where is this? You know, where is that? All right. Well, suppose that we say that this is the plot of w is equal to absolute value of 3t minus 7, like so.
You have to set it equal to 0.
Mm-hmm. So then, if that's the case, that the vertical, you know, that we're calling the vertical variable w, then what's the equation of this? This would be w equal 0, right? So the equation of this line would be w equal to 0. So what we want is we have two plots. We've got the plot of the red, w equal absolute value 3t minus 7, and we've got the plot of the graphite, w equals 0. We want to find the intersection of w equal 3t minus 7 and w equal to 0. So the way that works is, yes, you solve an equation. Is you want this kind of w, this red w, to be the same as this graphite w. So you want the w's to be the same. So therefore, we need to solve absolute value 3t minus 7 equal 0, because it is this right-hand side equal to that right-hand side. All right.
We did not put the lines when we do that equation at each points off. Because it's all going to come out to the same number, right, since it's going to 0.
Okay, so let's talk about that for a second. So in the end, we're solving an equation that kind of looks like this, right? And the question is that what could I possibly be concealing so that this equation would be true?
Looking for t equals to make sure that that equation equals 0.
I know, but ignoring t,
Okay.
ignoring t altogether. So like you know, if I was concealing like a giraffe, this would be false, right? Because absolute value of giraffe, what does that even mean? Okay? If I was concealing a 2, this equation at least could make some kind of sense, but it would be false, because the absolute value of 2 is in fact not equal to 0. If I was concealing a negative 3, the equation would still be false. What possibly could I be concealing so that this equation could be true? A 0, that's it. That's the only thing I could possibly be concealing. So whatever it is that I'm covering up, it's got to be 0. So the next step is to write, oh yeah, that thing, in fact, it must be 0 in order for us to proceed. So I think what you're asking is that, would it be okay to just do that?
Yeah.
And on this exercise, more or less, yes, but I'll give you some where that won't work, essentially. Good, and now this is an equation y'all could have solved, you know, long ago. So then the answer is 7/3. And to give you, you know, me mainly, some notion of scale, this is 2.3 repeating. Okay, so it's between 2 and 3. So that's where this is. It's between 2 and 3. All right, so now that's a sketch of what this looks like. So now let's sketch the region / shape that this integral is referring to. So, well, we've established that that's about 2.3. So the origin must be somewhere over here to the left, in fact. Then so this here, that's about, that is, t is 2.3 repeating. And then, so what shape is it that this integral is referring to? What further amendments do I need to make to the sketch to finish it up? Yeah, the bars. Okay, so then at 1, so if that's 2, then this is about 1 here, and this is about 4. So that's about, you know, t is 4, and this is about t is 1. So the shape that we're talking about is this. Okay, and well, you know, if the instructions were different, you could now, you know, say, well, forget the FTC. I'm just going to measure the stuff, right? You just, you know, plug in 4 and determine that's, well, 3 times 4 is 12, minus 7 is 5, so this is height 5. And that width is, you know, 1.66666666 or whatever. And you could do that. But it says to use the FTC. All right. So just like on the previous exercise, we're going to need to split the integral into 2. But where's the split going to occur now? At 2.3, right? It's gonna right there at that place where the function changes its mind. Okay. Good. So then, that means that we're going to take the original integral, 1 to 4, absolute value 3t minus 7 dt, and we're going to split it at 2.3 repeating 3t minus 7 dt plus integral 2.3 repeating for absolute value 3t minus 7 dt. Okay. Then, now, remember, the purpose of the split, you know, sort of like some overriding thing, besides the fact that it says to use the fundamental theorem of calculus. Besides that, sort of the overriding purpose is you want to rid yourself of the absolute value. It's like causing us grief. So it's still there. Now we want to be rid of it.
We know the right's positive and the left's negative.
Okay, what do you mean?
Because that's when the change happens. So it's 1.5 and 2.3 is because it's positive, going from 2.3 to 4.
Mm-hmm.
And it's negative going from 2.3 to 1. So
Okay.
we need that to be negative sign. Right?
Okay, so it sounds like you're saying the right thing, but now we've got to, we've got to write down the right thing. Okay, so then, so like this one, say, this one on the right. So 2.3 repeating to 4, and dt. And what is it that I'm supposed to write down there?
Just 3t minus 7.
3t minus 7. Okay, good. Because, for example, one of the numbers that's in here between 2.3 repeating and 4 is how about 3? 3's in there, right? So then consider the expression right here. If t is 3, that'd be 3 times 3 is 9 minus 7 is 2, and the absolute value of 2 is just 2. Right? Absolute value says, yeah, just pass on by. I don't need to do anything to you. You're a 2. You're fine. The same story will be true about, say, 3.1. If instead of plugging in 3, which is what we just did, if we plug in 3.1, it'll be the same story. So absolute value is not going to do anything here to that. All right. So 1 to 2.3 repeating, we will still have dt. And what gets put here?
In quotation, 3t minus 7 and negative on the outside.
Right. To parenthesize it like so. 3t minus 7. So it'll be just exactly that, except with a negative right there. Because, for example, a number between 1 and 2.3 would be something like 2. So if we plug in t as 2, that'd be 3 times 2 is 6, minus 7 is negative 1, and absolute value is going to negate that, right? So what I'm saying is that the reason why this is going to work this way is you can look at this function, absolute value of 3t minus 7, and you can write it in this way. You can say, okay, remember what absolute value does. Whatever I'm covering up, absolute value is either going to output exactly what I'm covering up or the negation of what I'm covering up. So if I'm covering like a p, then the choices are going to be p and negative p. Those are the choices. So the choices are (3t minus 7) and negative 3t minus 7. Those are the two choices, because it's always going to be the thing or negative the thing. Then the question is that we need to ask ourselves, or just repeat again, is that for what t's, values of t, are we going to pick this one? Right. T is greater than or equal to 2.3 repeating. That's this one. And this one is the alternative. So now, to hopefully not hit it entirely too hard, what I'm saying is that if you were on this red world right here, and you were far away from the pointy spot, then the equation for your world, as far as you could tell, would be W equal 3t minus 7. That's what your world would look like. That's what the equation for your world would be. If you were a little bitty creature living on the red world and far away from the pointy spot. Whereas if you were a little bitty creature living on the red world, far away from the pointy spot, but on the left side, what would the equation for your world be? W is negative 3t minus 7, like so. Okay? So now I'm hitting this really hard and repeating myself a lot, I admit. Well, that's just one of the biggest tools that teachers have, is just to keep saying the same thing over and over again. Because I find that this, many students find this idea slippery. Good. But any question getting here? All right. So then I'm going to spend this negative. Because I don't want to like leave it hanging around. So I can either distribute the negative into this, or I can flip the order of the thingies, whichever way, but I want to be rid of it. So do y'all want me to flip the order of integration, or do you want me to distribute this in? Distribute? Okay, doesn't matter to me. Fine, so this will be integral 1 to 2.3. Repeating, and then when you distribute the negative in, I'll write it as 7 minus 3t. Uh, 2.3 repeating to 4, and then 3t minus 7 dt. So we've made it, right? We dispensed with the absolute value, and now we can use the fundamental theorem. So what is the antiderivative of 7 minus 3t with respect to t? Mm-hmm. Very good. So 7t minus, and I'll write it as 3/2 t squared. And then this from 1 to 2.3 repeating. Then a similar thing for the next one, 3/2 t squared minus 7t from 2.3 repeating to 4. Any question getting to here? And now this is like supremely boring, so I'm just going to rush through the next part. But this would be a good opportunity, I think, for you to do some calculator gymnastics. So I'm going to do it real quick. So to plug this in to the calculator, in fact, I'll do it on the next page. So to plug that into the calculator is something like this. So I'll write it out a little bit. So 7 multiplied by 2.3 repeating minus 3/2 times, oops, times 2.3 repeating, square that. So that's that, and then minus 7 times 1 minus 3/2 times 1 squared. So that's the first thing there. The second one would be plus that thing evaluated at 4. And I'm going to make an error here. And I want someone to, I want you to, I'm going to, what am I trying to say? I'm going to make a deliberate error here. And I want you to, I want to show you where I can see, assuredly, I must have made an error. So it's like a way to check your work. So now I'm trying to make a specific error, but not any others. We'll see. Blah, blah. Okay, good. Like this. All right, so my error is in place, but now I'm going to start figuring out how to do this with the calculator. So like, all right, calculator gymnastics. To get this, I'll do just this one in the calculator, then just that one in the calculator. So to get your calculator to do this right here, at least if you have a style of calculator that's fairly similar to this one. The way that you can do that is by typing something like 7 multiply, and then I put a parentheses around that in front, right? 7 multiply, and then, well, there's no repeating button, so you just type a bunch of 3's. So 7 times 2 point, and I'll type like 6 3's. Okay, 7 times that, and then minus 3 divide 2 multiply 2.33333 caret 2. Remembering that caret is the punctuation for exponent. Okay, close parentheses. That's just that bit there. Minus 7. You know, if I was really typing this, I probably wouldn't type times 1, but okay. Minus 3 divide 2 multiply 1. Whoops, caret 2, like that. So that's what you'd have to type into the machine to get it to work out. And a similar thing down here. Okay, so I'm going to type those in. And I'm going to fill in these 2 boxes. So it's going to be some box, and then plus other box. Okay, so for this first thing, that one, I get it looks like 2.6 repeating. So that's what goes in the first box. So now I'm going to type this in. Three halves times 4 squared minus 7 times 4 plus 3 over 2 times 2 point lots of 3's squared minus 7 times 2 point lots of 3's.
You made it a plus.
Made what a plus?
You made the thing right there.
Okay, well, just a second. No, look, it is a plus. Look, see, it's a plus.
Oh, okay.
No. No. So I typed this into the calculator, okay, as it's written. And when I type it into the calculator, what I see is my calculator reports this number, negative 12 point whatever, negative 12.16, and that 6 appears to be repeating. So I claim that having looked at that, this is surely not right. This couldn't conceivably be correct. Why not? I claim that there's like a conceptual problem with this number, negative 12.16.
Oh, this is plus instead of minus.
Well, yes, I understand that, but that's not what I'm talking about. I'm saying that this number on its face, in and of itself,
It should be positive.
it's got to be positive. Why is the answer got to be positive?
Because that's how it is.
That's the area of this triangle, right? That's the area of this triangle. That's what it's supposed to be. It couldn't possibly be negative 12-ish. So this is a pretty minor error, right? Like literally a single pencil stroke, right? That could happen to anyone. Okay, but what I'm saying is that when you understand what's happening, when you understand the meaning of what these things are talking about, you should look at an answer that's surely got to be positive. But you type something into the calculator and got something negative. Now it's time to go fishing for where that problem is, right? And it can be the other way around too, right? It can be that well, you're expecting to have a negative answer because, for example, you're integrating a function that is below the x-axis. Well, then you're expecting to have a negative answer. And if you type something into the calculator and get something positive, it's time to go fishing, right? Okay, so then this couldn't possibly be right. In the end, this needs to be minus, right? It needs to be minus because the fundamental theorem says that you're trading those infinitely many evaluations of little f for exactly 2 evaluations of big F. And what are you supposed to do with those 2 evaluations? You're going to subtract them, right? Okay, good. So, you know, editing what I typed into the calculator here, blah, 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 right there, change that to a minus. And I get 4.1 appears to be a repeating 6. Okay, now that seems reasonable to me. In the first place, at least it's positive. And furthermore, from the picture, okay, because I tried to draw it at least a little bit reasonably, it appears to me that that triangle should be a little bigger than the other one. All right, seems reasonable. So let's, let's do that. So then plus 2 point lots of 6s. 6.8, 3333 appears to be a repeating 3. Good. Any question about this one? All right, let's do another one. Got to get real comfortable with this absolute value thing. All right, so now let's, this is me back in my office conspiring to make an exercise. Okay, so I want a parabola that is sometimes above the x-axis, sometimes below. The x-axis. So what I mean is that, I want a parabola that does this. So if that's the x-axis, then I want it to be like this. One of these. So the question is, Well, how can I come up with one? All right. Well, these things, because this is the x-axis, these are called x-intercepts, right? Because that's where the thing is touching, right? The x-axis. And it is one of the facts of college algebra that we want you to know that concerning polynomials. X-intercepts, another name for these is zeros, because after all, if this is the plot of y is f of x, then at what height is the x-axis? 0. So these places where, where inputs produce an output of 0, those are called zeros. That doesn't mean that they occur at 0. That means that when you plug in one of those values, you get 0. So let's choose some numbers for the zeros. Let's say, just for sake of argument, let's make this one 1, so that when you plug in 1, you get 0. And what do you want that one to be? 5? All right, fine. And we want a quadratic that'll do this. And here's the last bit of knowledge that you need to know from college algebra, and that is that these zeros, 1 is a 0 because when you plug in 1, 0 is output, and 5 is a 0 because when you plug in 5, 0 is output. Zeros are always in correspondence to factors, which means that if 5 is a 0, what's one of the factors? X minus 5. And if 1 is a 0, what's one of the factors? X minus 1. Which is to say that, x minus 5 needs to be one of the factors, and x minus 1 needs to be one of the factors. So have a look at this quadratic. What would you get if you plugged in 1? 0. What would you get if you plugged in 5? 0. Well, that's exactly what we're saying.
Just distribute it to the equation.
Yeah, that's it. Now, for reasons that won't be clear for at least another 90 seconds, I'm going to put a 6 right here. The reason for the 6 will be clear in a moment. Remember that what we're doing is we're making a hidden block where I'm conspiring with myself and y'all to make an exercise. Okay, so now I'm going to multiply this out and collect like terms. X squared minus 6x plus 5. So that'd be 6 x squared minus 36 x plus 30. Okay. So here's the question. Consider the integral from 0 to 7 of 6x squared minus 36 x plus 30 dx. So the first request is to sketch the area corresponding to this integral. Indicate which pieces have negative or positive area. So could you remind me, what's the rule? Under what circumstances does the integral count an area as being positive and when negative? When what? I just mean without no equations or anything like that. Just the integral counts some areas as being positive and counts other areas as being negative. And what's the rule? Which side of the x-axis? Right? So then if the area is above the x-axis, that area is counted positively. If the area is below the x-axis, that area is counted negatively. Yeah? I think your question will be answered as we do it. So what I mean is that I want you to sketch the area that this is talking about, and then point to each bit and say that bit is going to be counted positively, that bit's going to be counted negatively, etc. So that means that in order to do this, we need to make a sketch of y is equal to 6 x squared minus 36 x plus 30. Now everybody knows the best way to make a sketch of such a parabola is to factor it. Okay. I can see that 6 is a common factor, so I'll factor it out. Doing that, I get this. And then does that quadratic factor? Yeah. Yeah. Okay, it does. Amazing. It's almost like someone made it. X minus 1 multiplied by x minus 5. Okay, that's good. We factored it, and those factors are particularly useful for a sketch because we know that factors are in correspondence to what? The zeros, the intercepts, right? Furthermore, because this is a quadratic, we know that its plot is a parabola. So we know it's a parabola, we know where its zeros are, and furthermore, we know that its leading coefficient is 6. So that tells us whether or not it opens down or up. So which one? It opens up, because 6 is positive, right? And this is a smile. Positive people are smiling. So we know a great deal about this thing, in fact. It looks like this. So we've got 2 intercepts. There's an intercept at 1, another one at 5. And then the parabola does something like this. And if this all seems a bit forced and tedious, having that right there, then welcome to my world. This is what it's like. All right, so then this sketch, in the end, the question was to sketch the area corresponding to this integral. So we don't quite have it yet, as further stuff is needed. What do we need? 0 to 7, right? So we need to mark out 0 and 7. So here's 0. And here's 7-ish. Okay, so then 0 and 7 are now marked, and then the question is okay, we've got the quadratic plotted, we've got x equals 0 plotted, x equals 7 plotted. What are we talking about? What shape? I want to let me say it like this. I want to shade something in. What is it I'm supposed to shade in? Like this? This one? And also the one below. Yeah. This one. So it's all of that. But now, the second bit of the instruction. Indicate which pieces have negative or positive area. Well, which ones have a positive area? The ones above the x-axis. those ones will be counted in the positive sense. And the one below has a negative area. So now, just looking at it, especially the way I drew it, it's not entirely clear if, when you integrate it, well, we're going to get a number, but should that number be negative or positive? It's not entirely clear from the picture. In the end, the question is sort of asking, did it come to pass that there was more above, or was there more below? You can think of it like a tug of war. Okay, and I'm not such an excellent artist. You know, maybe I didn't do it just right. So it's not entirely clear should the answer be negative or positive, because some of the stuff is positive, some of the stuff is negative. It's going to turn out that it's going to be overwhelmingly positive, in fact, because, well, this thing is extremely steep, and this piece is enormous, in fact. but well, I just know that from experience. But what I'm telling you is that from this picture, it's not entirely clear should the answer be negative or positive. Good. Any question about this? Okay, so now let's evaluate the integral. Well, that turns out to be not a big deal, really, because, well, can you use the fundamental theorem? Yeah. So let's just do that. All right. So we can do it term by term. What is the antiderivative of that term? 2x cubed. And how'd you get that? The power rule. Good. It would have been 6x cubed over 3, but the 6 over 3 canceled to be 2. That's nice. Then minus, what's the antiderivative of that term? Okay, 18x squared. And how'd you get that? Yeah, 36 over 2. Oh, that canceled too? Oh, that's nice. Why did I multiply by 6?
So you can allow all.
So there wouldn't be any fractions when we're at the end dealing with this mess, right?
Could we, are we able to like do that on our own?
No. It has to be it has to be given to you thus. No, I mean I did that just because I don't like dealing with the arithmetic at the end. I think that's the boring part. I mean, some things are important, like to know whether or not it makes sense for this answer to be negative or positive, right? And just like the general size of something. Should it be in the tens or tens of millions? Okay, so then the antiderivative of that term is 30x. And then from 0 to 7, 0 is another gift. Why is that? Yeah, good. So then, fine. In the end, we need to evaluate this kind of thing. 2 multiplied by 7 cubed minus 18 multiplied by 7 squared plus 30 multiplied by 7 and then minus 0. Really? 2, 7 cubed, 18. No, it's positive, but not nearly as positive as I expected it to be. Yeah. So I get 14. I was expecting it to be like 100 or something like that. Yeah?
I have a question. The problem before this, we did it with pieces.
Uh-huh.
So in this particular problem, why wouldn't it have been, the derivative from 0 to 1 minus,
Okay, so there's a couple ways to think about it. One way to think about that question is that, so for example, going back to even this one. Let's go back to the one you said. So we wanted to do this. now is the absolute value among the blessed three antiderivatives that we know? It's not, right? So we've got to kind of like work to get it to be, to get it to right here. Finally, when we discover, the magic split is at 2-point repeating 3, and what makes that one particularly nice is that that means we can replace this absolute value with that, and that one with that. And then, from there, we can use the fundamental theorem on each one. So now, for this one, well, there was nothing standing in our way to begin with for just using the fundamental theorem. And, well, you might be concerned, like, well, some of the stuff is under the axis, and some of it's above. Well, you don't need to do anything special, like, you can think of it like keeping track of the money in a till. So, when you're pulling money in, it's just adding. But when money's leaving, it's also adding negative amounts. So all that this is doing, you can think of it like what the integral is doing, is it's adding stuff up, and when it's in this region, the sum is going up, and when it's over here, the sum is going down, and when it's over here, the sum is going back up, and it scans all the way from 0 to 7, and the balance is 14 at the end of time. Yeah?
So you were saying that, because you could assume just looking at it as a concave, that it would be positive. I know you have to go through all the steps.
That what would be positive?
That would be
Are you asking why I thought the answer would be positive?
well, right, well, I'm saying you just, because it just appears like it would be positive, like the graph.
Right. All I'm saying is that plots drawn by hand, just like a fast and ready plot, can be a little deceiving.
Okay.
That's all that I mean. I mean, I agree. Even to my eye, it appears that it should be positive. But I'm just, be careful looking at a by hand sketch. Is all I mean. So let's continue this exercise a little bit. So, how about 3? If we write, how about this? I'll say it this way. Please sketch y is the absolute value of 6 x squared minus 36 x plus 30. So we more or less sketched this thing, but without the absolute value on the previous page, right? Like there and there. So the original one is like this. 2 points, 1 and 5, parabola. So this one here is the plot of y is 6 x squared minus 36 x plus 30. Okay, and then my question is what, that's what it looks like before we send the right-hand side through the absolute value. What will it look like after? Yeah, it'd be, kind of like a W, a little bit. So let's consider here for a moment. Absolute value, the name of the thing that you put into the other thing, like what I mean is you look at the definition of absolute value like this. The name of the thing that's being put inside of the absolute value is argument. Like that's the technical name, right? And so I'm going to start using that word because it's easier to say than thing that you put in the thing, right? So So the absolute value of an argument is either the argument itself or the negation of the argument. So if the argument was positive, then it just passes right through with no alteration. But if the argument is negative, then it gets negated when it passes through the absolute value. So notice that over here, what is the output? Is the output negative or positive over here? It's positive right here. You can see that the y value is positive because it's above the axis. Okay, so for example, 0 is like right there. If you were to plug in x is 0, that would be 0 minus 0, which is 0, and then plus 30. So like right here, that's at height 30, right there. Right? But a number that's between 1 and 5, how about 2, say? 2 is between 1 and 5. If we plug in 2 here, that'd be 2 squared is 4 times 6 is 24. 24 minus 72 is negative 48. And then negative 48 plus 30 is something negative, right? So in here, all the y values are below the x-axis, they're negative. So let's be real specific. So here is x is 2, and right there, that y value would be, let me type it in just to make sure. 6 times 2 squared minus 36 times 2 plus 30. So negative 18. So that y value is negative 18. So what we're saying is that I want you to do exactly the same thing, except after you calculate that polynomial, then I want you to go ahead and push it through the absolute value. So if you push that to negative 18 through the absolute value, it would become what?
Positive, so basically you're just getting the entire area of everything that's highlighted, versus the other way, it was taking it away.
Right. So and specifically the way the plot will look is it'll be just like this. So like this this negative 18 will be flipped up to positive 18, and this, I don't know, negative 20 will be flipped up to positive 20, etc. So the way it'll look is like this. We'll still have these notable points, 1 and 5. And because this whole right arm is above the axis, the absolute value says, pass on by, go right ahead, you're fine. And because the left arm is also above, that meaning that those are already positive, the absolute value is going to say, yeah, go right ahead. But the part in the middle, it's going to take it and flip it up. So it'll look like this. Any question about that? So, I hope I'm predictable enough for you to be able to predict what my next question is. Now please evaluate the integral from 0 to 7. Absolute value, 6x squared minus 36x plus 30 dx. So, this question is meant to prime you for this one. So what does this sketch have to do with this? Right. So what's happening is that, this sketch, we could take that sketch, one, 5. Like that. And then, put 0 here. Like this. and 7. And now we're talking about this. And now, of the three sort of obvious pieces, 1, 2, 3, which of them are going to be reckoned to negative and which of them reckoned to positive? All positive, right? That's the effect of having mashed the thing through absolute value before you gave it to the integral, right? You said, well, I'm going to make everything be positive. Okay, that's fine. So then if we want to, be able to do this now, we really will have to do the splitting bit, right? Because here's the thing, is that absolute value of argument is always either argument itself or negation of argument. So what I'm telling you is that the left and right arms are the same as the original. No problem. So what I mean is that if you were a little creature living in this red world, if you were on the left arm or the right arm, that would be just like being on that, being on this. It's just the same. But what if you were in the middle? If you were a little creature, living right there, then what would be the formula for your world? Well, that's for the whole thing. What I mean is, how could we write the formula for if you were right here, but without absolute value? Not quite. Yeah, negative all that. Negative all that. Because it'd be negative 6x squared minus 36x plus 30. Because the absolute value, to flip it up, it negated it. So in order to evaluate this with the fundamental theorem, we'll have to break this integral into three pieces. So what is the first interval? 0 to 1. So it'll be 0 to 1, absolute value, 6x squared minus 36x plus 30 dx. Yeah, I'll drop it in a second. I'm just want baby steps, right? And then plus the next interval, 1 to 5, absolute value, 6x squared minus 36x plus 30 dx. And then 5 to 7. Absolute value, 6x squared minus 36x plus 30 dx. So then we split it into three pieces. And now, for each one of these pieces, we know what it takes to drop the absolute value. So on the left piece, in fact, we can just drop it, right? There's nothing, it's doing the exact same thing, no changes. So this would be integral 0 to 1, 6x squared minus 36x plus 30 dx. Okay? How about the middle piece? What does it take to drop it? Yeah, negative all that stuff. So plus negative all that. Okay, and then plus 5 to 7. So now I'll leave this to y'all, right? That's super duper boring to try and do. But I hope we can agree that we could do it, right? Using the fundamental theorem. Good. So now this view like this might be something like we're trying to keep track of the amount of money in a till, in a register, so that some of the time money's being put in so that the sum is going up, some of the time money's being taken out so that the sum's going down, up, etc. But this, where you take it doesn't matter what direction the money's going, whoever's doing this counting is counting no matter what. Well, that's like the banks. That's what they do, right? It doesn't matter which way the money's going, right? A to B, B to A, they're taking their cut. Well, I guess maybe a better example would be something like the credit card companies, right? Because you've got transaction fees, right? They don't care who's paying who, as long as someone is doing the paying, because they want their cut. Yeah?
Is that in non-accounting?
Yeah. Well, I mean, it's not to be too down on the financial merchants. I mean, they offer a valuable service, but sometimes it cuts a little deep. Okay, good. Any questions about all that?
So, because you are changing it almost fundamentally, because it's by having, it almost is wrong, because you have the way it should be, and then because you put the absolute value, you're completely changing it.
Yeah, it's just a completely different exercise.
Okay.
It's a completely different exercise. Yeah, it's just a completely different one. It's the difference between like let's keep track of the amount of money in the register, or let's imagine that we make 3% on all transactions without regard to the direction. Then in such a case, then you would use something like absolute value. Okay, good. So to answer your question, you had a question, but now I'm meandering my way back to it. The integral actually does something really nice for us. It allows us to make functions in a way that we've never made them before. Well, until, they've been made this way for hundreds of years. But I mean, in our class, we haven't made a function in the following kind of way. So let's consider, for example, define f of x equal to the integral from 1 to x of 1 over t dt. So now, in order to evaluate this function, in order to plug in an x, you've got to evaluate an integral. And this is only for positive x's. So let's think about this for a minute. This really isn't an exercise, it's more like a remark. So now, what does the plot of 1 over t dt look like? So can you remember? So if this is t and this is y, then what does the plot of 1 over t look like? It will, as t gets big, yeah. And, well, when t is positive but small, then 1 over t is positive and big. So like 1 over 1 is 1. 1 over 0.1 is 10. 1 over 0.01 is 100, etc. So the right side of this plot will look like this. And the left side like this. So the name of this shape is hyperbola. So that's its name. So this is the plot of 1 over t. That's what 1 over t looks like. Now the function f of x is the integral of that function from 1 to x. So what that means is that in order to understand what f of x is, it's actually the area under the curve. So therefore we can say the integral from 1 to x of 1 over t dt actually looks like this. And because we have the restriction that x is positive, I'll just ignore the left side of the plot. So 1 over t kind of looks like this. Here I'll draw 1. And then suppose that like x is some number that's more than 1. Then what is this referring to? Yeah, that area there, right? So this is this. That's interesting. So what I'm saying is that if you take this x and drag it to the right a little bit, can you see that I'll sweep out a little more area? So that means that if I make the input to f a little bigger, then the output will be a little bigger because I'll. All right. So I have a question. What about because this is f of x? What is f of 1? Remember, x is the name of this fence post. So what I'm saying is that suppose I grab this fence post and I move it over to be on top of 1. Then how much area would be between 1 and 1? 0, right? Oh, that's interesting. Now here's another bit. What if we wanted to solve f of x is equal to 1? Which is to say that I want to know the x. At what position would I need to put the x so that the area that's shaded in is exactly 1? You know, if this is not enough, I need to move it to the right, and if this is too much, I need to move it to the left. Where do I need to put this x so that the area is exactly 1? So can anyone tell from looking yet? I'm trying not to spoil the surprise. Well, I mean, you can't tell from the picture. What I'm saying is that can you tell from the definition what x you'd have to put in so that the output would be 1? And the answer is going to be the natural number e. Why is that going to be the answer? Well, let's think about it. Can you actually integrate that? 1 over t dt? That's t to exponent negative 1. What rule is that? That's the log rule. F of x is the integral from 1 to x of 1 over t dt. 1 over t dt. But that would be the logarithm of the absolute value of t from 1 to x, according to our rules. And so and the fundamental theorem says that this would be natural log of the absolute value of x minus natural log of the absolute value of 1 But what is the log of 1?
Like in this case, x is the number.
X is the input to the function, yeah.
Oh,
So what's the log of 1? 0. Log of 1 is 0, and we just said that x is positive. So that means that if x is positive, what's the absolute value of x? Just x. So what I'm telling you is that this whole page is that this is actually the definition of the logarithm of x. It's the integral from 1 to x of 1 over t dt. This is what it is. This is how you calculate it. That's its definition. So, yes?
So that's the whole reason. There's something
This whole page. The purpose that I wanted to see, because he brought up a question of what happens, sort of. His question was kind of like, what if I have a fence post where I can move it around and it's the amount of area? What I'm telling you is that now we can define functions thusly, right? This function is defined as an integral, where the input is wherever you want it, like one of the boundaries. Beautiful. So this is actually the definition of the logarithm of x. Okay, great. I'll have to see what I can. I only did that page because you asked a question, but that's just to like pique your interest, to show you that there's a wide world out there.
Does that become a good question? Why is it started with 1?
Because in the end, there's some good reasons to make it be that way, but in the end, logarithm was figured out like what am I trying to say? We look at the natural world and we see patterns all over the place. And, it came to pass that we found out that, wow, these particular kinds of spirals, logarithmic spirals, are showing up all over the place. Right? Like sea creatures have it in their shells, and that broccoli has it, that galaxy over there has it. This must be a thing, And so, then we said, well, we're going to name that thing, and call it logarithm. And then after the fact of doing all that, we started figuring out calculus, and we wanted to make stuff rigorous. Then we said, okay, here's going to be the definition of the logarithm, and here it is. So, from a mathematician's point of view, I can just say it's that way because I say, because that's like the definition. But that's not very historical, right? In fact, lots of looking at the natural world around us and observing, oh, look, it's everywhere. Patterns that are made, that are described by this function.
So if you did this integral from 0 to x, you just get really stupid numbers.
Well, in fact, for that specific example, you wouldn't get any number whatsoever. And the reason is because what you're saying is that what if you moved this fence post over here? So if you moved the 1 somewhere else, it would not be logarithm. It would be kind of like almost logarithm. But in fact, if you were to move this 1 over to 0, then you'd be asking, to add in all of this area right here. And actually, there's infinitely much area in there. So if you were to integrate from 0 to any other number, the answer would be infinite. So you wouldn't get any number at all. Other questions? Okay. So now, let's do some, let's drop the absolute value thing for a little bit and put that kind of firmly. I want to let some of those ideas sit and stew so that they're ready for Thursday. So now I'm going to change gears to something else. Let's do one like the following. So the only instruction is just evaluate. So the integral from 1 to 2 of the log of w over w dw. All right. So, well, we'd like to use the fundamental theorem. That'd be terrific. So then, supposing we're going to do the fundamental theorem, we have to ask ourselves, can we anti-differentiate this? Do we know how to do it? Okay, so we need to start at the top of the Riesz procedure, right? Which is to say, okay, well, if we're going to try to anti-differentiate this, does it happen to be the case that this is exactly one of the blessed three? It's not. All right. Can we perform some algebraic operations to make it be one of the three? I would say it doesn't appear to, right? It doesn't. We can't like distribute some stuff. I don't see. So then, what's the next step? Draw a picture would. Well, I mean, that's always a good idea. Usually a good idea. But in the Riesz procedure, what's the next step? If you can't do something algebraic, then what? Yeah, can you do a substitution? Okay, so, right now we're considering a substitution. Substitution. And remember that the beginning of wisdom is calling things by their proper name. So, what is the proper name for substitution? Right, a variable differential substitution. So I just keep saying that because, well, I don't want anyone to make the mistake of leaving out the differential part. That's what usually gets left out. Okay, now a variable differential substitution, what it's undoing, it's undoing the chain rule. So the chain rule, when you do it, you'll have a thing and the derivative of same thing, and you'll have them multiplied. So what I would like for you to do is I'd like for you to look at this and see if you can pick out something where the derivative of that same thing is also present. And sometimes when you're considering this kind of thing, it can be helpful to just write things in different ways. So for example, like this. So instead of writing division by w, I write it as multiplication by 1 over w. So, can you pick out anything that this thing and also its derivative appear? Okay, what do you mean? I need a thing and its derivative. Okay, so which one is the thing and which one is the derivative of the thing?
W to negative 1 gives you 1 derivative ln w.
Okay, so this is the one. So
that's the derivative of the one on the right.
okay, wait. I'm not sure we're saying the same thing.
All right. If you were to take w to negative 1 d dw, you get ln.
I disagree.
Derivative of another w.
The derivative of logarithm, derivative, is 1 over w.
So I got these guys.
Okay, good. So you just gotta, it's kind of, well, it's just an unfortunate feature of this area of calculus is that we've got this operation and it goes forward and backwards, and you've got to know when you're doing what. So derivative of logarithm is 1 over w. So we'll try a substitution. How about y is equal to the logarithm of w? So this, remember the name of this is a variable differential substitution. So this is the variable that we are putting on offer. We're checking to see, do we want to do this? So in order to confirm or deny whether or not we want to do this, we need to find the differential part of the substitution. How do we do that? Right? So dy dw would be 1 over w, like so. And then we want to solve for dy. So dy is 1 over w dw. So that's looking pretty good, I claim. So this is the differential part. So what's on offer is that we'll substitute this variable for this. So the reds will substitute like so. And the greens will substitute like so. So in particular, what's happening is that all the W stuff is being turned into Y stuff. But in fact, even here, there is yet more W stuff that hasn't been changed yet. So what other W stuff is not accounted for? So it kind of looks like I boxed all the stuff that has W. Doesn't look like I left anything off. But something's left off. What's left off is that this integration right here, ignoring all this stuff, this integration is occurring with respect to variable W. On what interval is it occurring? From 1 to 2. So what's going between 1s and 2s? Is that like giraffes or? No, it's W's, right? Its W's are between 1 and 2. So in fact, this 1 has something to do with W, and this 2 has something to do with W also. What I mean to say is that perhaps a more clear way to write this would be to write W is 1, W is 2, logarithm of W, 1 over W dW. So that, we're covering this and this. And then can you see now what has yet to be covered? The limits, right? So if we're going to change W's to Y's, then we need to change these limits also. Okay. So the question is that what is Y when W is 1? Right, so Y evaluated at W as 1, that would be logarithm of 1, right? Which is 0, as you say. And then what is Y when W is the other number, 2? Just the log of 2, yeah. And that doesn't simplify to anything nice. So, what I'm saying is that these numbers right here are replacing these numbers. So now can you see, yes, now we have all the W stuff covered. Okay, now there's if you've taken a calculus course before, besides this one, that included integration, you might have seen a slightly different way. I'm going to do that slightly different way on the next page, just to preempt any questions. Okay, but besides that matter, the new integral is then what? So it'll be integral, and then what are the limits? Very good. And then what are we integrating? Yes? dy? Right, the red box became y, the green box became dy, and then the limits changed as written. So that now we've significantly altered the original integral. And after every significant alteration, it's a good idea to start back at the top of the procedure, reach procedure, and ask, is this exactly one of the antiderivatives that we know? Now the answer is yes. So which one is it? The power rule with what exponent? 1. So this would be y squared over 2 evaluated from 0 to log 2. So then this would be log 2 squared over 2, and then I'll just write subtract 0 because that it's going to be 0. Any question about this one? So now, when we were doing antiderivatives, can you remember doing the substitutions? And then when we were doing substitutions, I'd always ask, so is this the answer to the question? And we'd all say, no. And then I'd say, why is this not the answer to the question? Because you have to put it back in terms of all one, you know, that one. Okay, so then you can answer this kind of integral in a similar way, and it still has that same back and forth structure. So now I'm going to answer the same question, except I'm going to do it slightly different. So here, this bit right here, this is the variable differential substitution, and this is where I changed the limits. So what I'm going to do is I'm going to solve this exercise again, but without playing with the limits. So, but before I go about doing that, I'll just say the following. So, if you're going to ignore one of these, ignore the one I'm about to do. You know, if you're going to say, forget it, I'm just going to pick one, pick this one. Okay. Several reasons to pick this one. Well, in my experience, students who take this way have a lower probability of error. Like it seems to be that the results are more accurate with this case. Another reasonable reason to go with this is that if you decide to go on to more exciting things that involve calculus, you know, because there's lots of stuff like, you know, like economics and all manner of science that involves calculus, and you're doing related but more complicated things, you more or less have to do it in a way that basically is this way. Like you can't do it this other way. It doesn't work. The only reason to do this is because I know that some of you might have taken a previous calculus course, and if you look at if you look at the textbook or other things, you'll see them doing this. So I don't want you to think that this is some kind of mysterious or secret thing. All right. Integral 1 to 2 log w over w dw. So same exercise as before, and solved in largely the same way. So we could write this as 1 to 2 log w 1 over w dw, same as before, and then do the substitution. How about you know, z is logarithm of w, dz dw is 1 over w, so dz is 1 over w dw. So again, we've accounted for this variable, this change of variables, and we've accounted for this change of differentials. But instead of accounting for the limits here and now, I'm going to just like put that on pause and just proceed. So, but no limits. So then doing that, then it's the integral from 1 to 2, and then it'll be z dz. Now, here's the thing, and this is the reason why students, why I suspect students seem to make errors on this method. Here's the thing, strictly speaking, no error has been committed yet. But the integration is occurring with respect to symbol z. But these limits, 1 and 2, are not with respect to are not corresponding to z. What are they? They're w's. So you've kind of got things that are kind of like mixed up right now. Okay, so you've got z's going on and w's going on. Okay, but strictly speaking, no error has been committed yet. Okay, then we can use the power rule and write z squared over 2, because that's what that is, and then from 1 to 2. And again, that's z squared over 2, and that's w is 1, and w is 2.
So we have to replace the z with the L and W.
Yeah, so now, from z's, now we go back to w's. Now, in the sense of what I was talking about before, the danger is past, because this expression is in terms of w, and so are the limits. So now we're sort of, back in agreement, and then we can just plug stuff in. So log of w, not w, log of 2 squared over 2 minus log of 1 squared over 2. Of course, the log of 1 is 0, like we noticed on the previous page. So the answer is the same. Now, one of the most, when students take this method, one of the most common kinds of errors that I witness is that a student gets to this place and then does the following. They say, well, this will be 2. This will be 2 squared over 2, and then minus 1 squared over 2. So what went wrong?
They forgot to plug in the original.
Yeah, they plugged these w values into this z expression. Yeah. So if you're going to do this way, then okay, I won't try and stop you other than to encourage you not to. But if you're going to do it this way, I would strongly encourage you to write the following to save yourself from error. To write w is 1, and w is 2, and w is 1, and w is 2. Because while I've seen a lot of students do this, if those w's were not there, I've never seen them make this error if the w's are there. So, only you can decide what's best for you. Any question about this? So more or less from now on, I'm going to do it the other way. I might alternate a little bit.
Why doesn't that work with more complex problems?
Because, in the end, the reason is because in your mind's eye, imagine an interval. And now imagine what the boundary looks like. It's 2 points, right? Okay. Well, you can, an interval is a one-dimensional object, and it has a zero-dimensional boundary that consists of 2 points. Now, generally speaking, for example, like a three-dimensional object, it has a two-dimensional boundary. Right? So like I'm a three-dimensional object, and you don't have X-ray vision, so as far as you can tell, I'm full of like unicorns and magic and stuff, right? You can only see the boundary. Now my boundary is two-dimensional. Like you could walk around on it and it would be like two-dimensional. So in the end, the reason why is because in the specific case of a one-dimensional object, it has a zero-dimensional boundary, and that's a particularly easy situation. And that easiness of having a zero-dimensional object is what makes it possible to do it in those two ways. Generally speaking, if you're integrating a 5-dimensional object, but using its 4-dimensional boundary, you won't be able to you won't have these two alternate ways to do it. Good. That kind of thing that I just said is not relevant for our class. I only mention it because you ask. Good. We have time for one more. All right. How about the integral from 0 to 1 of, what am I doing here? Oh, yeah. A fraction exponential of 2t in the numerator, and then divide by 3 plus exponential of 2t, and then that all squared dt. And, just evaluate in the end is the request. Okay, so is this exactly one of the blessed three that we know? No, it's not. It's not the power rule, it's not the log rule, it's not the exponential rule. Right? It has exponentials in it, but that doesn't make it the exponential rule. Can we do some kind of algebraic something or other to it? Nah, there's nothing we can do. In the end, when you have something that looks like a divided by a sum, like a plus b and all that, that's not going to work. So when you have it over a sum, you can't really do much algebraically with that. So let's do a substitution. Remember, it's a variable differential substitution. So whatever we're going to select for the variable, we want also for the derivative of that same thing to show up. So what do you think? Okay, I agree. So in particular, I'm going to write this in a slightly more calculus-friendly fashion. I'm going to write this as and by the way, this might be a good idea, like especially when you're getting used to this. Just when you see stuff that looks like that, and you're looking at this integral and thinking, I'm kind of drawing a blank. It might be a good idea to just rewrite all the exponents as, instead of divisions, write them as negatives. What I mean is write it like this. So instead of writing this down there with exponent positive 2, I'll write it up here with exponent negative 2. And then multiplied by exponential of 2t dt. Okay, so then we want something and its derivative to show up. Well, I think the thing in there. What do you think?
I usually pick the longest one.
The longest one? That's also a good idea. I mean, on another matter of just like test-taking strategy, like you might as well just write something down, right, and then just try it. I mean, how much time could you possibly waste? Like 20 seconds? So let's write something down. How about x is equal to 3 plus the exponential of 2t. So is that the one y'all wanted? Okay, so then that's the variable part of the thing. So now we need to figure out how we're going to substitute differentials also. So then dx dt, well, what's the derivative of 3? 0. Right? The derivative is 0. And then plus, we need to calculate the derivative of this exponential. Well, not over. E to 2t, and then multiply by the derivative of 2t. Right? Why is this multiply by derivative of thing? What is that? That's the chain rule showing up, right? Yeah, good. So then this will be exponential of 2t and then multiply by 2. Okay, so then we can solve for dx and get exponential of 2t multiplied by 2 multiplied by dt. All right. So now that we've done that, now it's like we need to look at the aftermath and kind of think, well, did it work out? All right, so what we're saying is that here, this variable, x, is going to replace all this. So far, so good. What about the differential bit? Yeah, we need to divide by 2, right? Because we've got the exponential of 2t, that's going to work. We've got the dt, that's going to work. But currently, that 2 is extra. So let's divide by 2 and get it on the other side. So now we've got the variable part squared away. We've got the differential part squared away. That's good to go. And now finally I'll convert the limits. So what is x when t is 0? So we need to plug that in. So that's 3 plus the exponential of 0. What's the exponential of 0? It's 1. So this would be 4, right? And then what is x when t is 1? Well, that'd be 3 plus the exponential of 2. And, well, the exponential of 2 doesn't simplify to something nice. All right, Gesundheit. So that means that the new integral is integral of, well, this would be what? X to negative 2. That's the variable part. And then what's the differential part? Dx over 2. And what are the new limits? Yeah? To 3 plus e squared. Now 3 plus e squared may not be a very pleasing thing to your eyeball, to your eye, to your sensibilities, but it's just a number, right? So e is like about 2.7-ish, and so, 2.7 squared-ish, that's between, 4 and 9, and then add 3 more. It's okay. So then, just doing this part quickly because we're out of time, that's a division by 2. We can just leave it in place, if you like. And then we can use the power rule for this one. So this would be x to negative 1, divide by negative 1, and then multiply by half. Don't forget about that part. And then evaluate it from 4 to 3 plus e squared. I see some sadness.
You have to plug back in the 2 plus e to for x.
Yes, we have to, we've got to do more, yeah. So then I'll simplify this a little bit. I'll put, I'll put negative half in the front, so that takes care of that negative and that half, and then multiply by 1 over x, like that. Change that x to negative 1 to 1 over x, and then now 4 to 3 plus e squared. And then, so this would be, I'll do a nice trick here. Because that's a constant, I can just leave it factored out. I'll show you why it's okay to do that. So that'll be 1 over x, so that'll be 1 over 3 plus e squared minus 1 over 4.
For x.
Yeah?
To replace it with the 3 plus e.
No. No, I don't need to do the replacement because I did this. Right? If I had not done this, then I'd have to go back to t's. Right? So like, what I'm saying is that when I got to here, t's were dead to me.
Oh,
They're, they're,
yeah. Oh,
From-
because you use, oh, okay.
because I did this.
But the other way in.
Yes, if you were to do it, if we were to have done it, no? If we were to have done it this way, without changing the limits, we would have had to gone back to the original. But like I said, it's possible to do it that way, but I find that students make errors when they do that. So rather than doing it that way, it was all about t's until here, and then no more about t's now. Now it's only about x's. Did you have a question?
So, okay, so the final step that you just did,
Mm-hmm.
you have your, you factored out the negative.
Oh yeah, how did I do that? The reason is because suppose that I didn't do that. Suppose I did it as stated. Then it would be negative half multiplied by 1 over 3 plus e squared, right? And then minus negative half multiplied by 1 over 4, right? It would be this one minus that one. But these two terms have a common factor of negative half. And if you were to factor out the negative half, you'd have that. So generally speaking, this will be the last thing because we're like out of time here, is that if you do something like this, k multiplied by big F of x, evaluated from a to b, like that, where k is just some constant, then you can leave that constant factored out. It'll be k multiplied by f of b minus f of a. Like that.
So
Only when it's multiplied. And only when it's a constant. With respect to x, the variable at hand. Other questions? Okay, wonderful. So be prepared on Thursday because we're going to get back to something that is conceptually similar to that absolute value thingy we were dealing with.